This is a cross-section of a typical urinary drainage catheter. The balloon has not been placed yet. A small hole is punched through the inflation lumen as well as the drainage channel. Alternatively, the punched hole could be just through the drainage channel. Punching a hole through the lower drainage channel only is important for drainage channels with D cross-sections. A fine filament is threaded from the back end of the catheter through the drainage lumen and out the front. A previously prepared small tube is attached to the fine filament. It can be secured in place with a hole and a knot. The small tube is maneuvered into place underneath the valve and inflation port. This small tube is the stretch valve. A hollow rigid tube is secured to the back end of the fine filament. This anchor is pushed into the back hub of the drainage channel. Note the slack in the filament. The amount of slack dictates the amount of elongation before the small tube or stretch valve is pulled away from the drainage channels. The balloon is then glued in place. The catheter is packaged and sold in this configuration. A stretchable filament can be used instead of this fine slack filament. Alternatively, a small spring can be placed in the drainage lumen. The spring can be tethered to the anchor and the stretch valve. Here we show the catheter in the urinary bladder. The balloon is inflated with saline. The inflated urinary drainage catheter remains passive in the patient. In the event the catheter is pulled backwards by the patient or snagged and pulled backwards, the distance between the anchor and the stretch valve increases and the filament becomes taut. At a certain point, the stretch valve is moved to the right, which opens the drainage channels and allows fluid to drain from the balloon. Without the balloon inflated, the catheter is easily withdrawn from the bladder and urethra with no damage to the urethra. Here I'm holding a urinary drainage catheter, my left hand above the balloon, and my right hand is a fixture that emulates where the bladder joins the urethra. Here you see the balloon sitting in the fixture. This is the entire drainage catheter. Note that it's approximately 16 inches long. Here we see the hub end of the catheter. Coming out of the major drainage channel is a filament connected to the anchor. The anchor is pulled into the major drainage channel hub and held in place. It's then pushed in with a rod. The catheter is now ready to be tested. We expect at about 2 to 4 inches of elongation that the stretch valve will pull to the right and fluid will be discharged. Watch carefully as I stretch the catheter. At about 20 inches, the valve will release and you see the balloon deflate and the catheter fall through the hole in the fixture. This previous demonstration was in real time. Let's slow it down now. Here is the same video in slow motion. As I pull it from the hub, or I could pull it from the center of the shaft, it works there too. You'll begin to see at a certain point that fluid comes out of the balloon, about now, and the balloon releases through the hole in the fixture. Let's revisit the length of the filament from the anchor to the catheter. If you make this larger, say 7 inches, the catheter will elongate about 50% before the valve is pulled downward and balloon deflated. Alternatively, the stretch valve can be placed in the inflation lumen. Here is a close-up of the stretch valve in the inflation lumen. What we have shown here is a retrofit on an already made urinary drainage catheter. As we are not privy to how these catheters are made in production, we don't know if this method of retrofitting is the most optimum way of manufacturing the catheter. However, we are certain that clever manufacturing engineers can implement this process in their current manufacturing.